our plenary speaker, Professor Maciej Lewenstein from the Institute for Photonic Science, or for short ICPO, from Barcelona, Spain. And he is certainly one of the very distinguished members of various branches of atomic physics and photon interactions, and it's really great to have him as a speaker today. Let me give you a little bit of background. He is originally from Poland. He got his PhD from the University of Essen in 1983, working with Fritz Haake. He went back to Poland and got his habilitation for the Center of Theoretical Physics in Warsaw. After that, he spent 3 years with Roy Glauber at Harvard University, and I guess this was his entry into quantum optics. After that, returning again to Poland, he then spent in 1992 a year at the CA in Saclay in France, working among others with Anne Lullier. And that was certainly the starting point of his contribution to ultra-fast and ultra-strong laser matter interactions. One more visit, this time to Gila in 1994, brought him into contact with quantum information, cold atoms, and Bose-Einstein condensates, working there with Eric Cornell and Peter Zoller. In 1995, he took a position at CA at Saclay for 3 years. Then finally, University of Hanover was lucky enough to attract him to a chair at that university. And I remember vividly at the DPG meeting in 1998, when even the Prime Minister of Lower Saxony announced very proudly that they succeeded in attracting Maciej Lewenstein to Hanover. Finally, in 2005, he took his current position at the ICPO in Barcelona. Now, Maciej Lewenstein has an incredible diversity in his research, which is really astounding, and he made seminal contribution, or nowadays you would say highly cited contributions, in very many different branches of physics, starting from mathematical foundations of quantum information theory, continuing with work on cold atoms and Bose-Einstein condensates, and in the field of ultra-fast and ultra-strong laser matter interactions. Everyone working in this field knows about the Lewenstein model, which really is the cornerstone of our understanding of high harmonic generation. So his breadth of activity does not stop there. He even has important contribution to application of physical models to human cognition, and even more interesting, to social psychology of voting behavior. And if that's not broad enough, he is also author on a book on Polish jazz recordings, which is one of his pastimes, and he's an avid collector of those. With all these important contributions he made, he got many prizes and awards, and I will not go through the long list of awards he has received, just to mention a few. He got elected Fellow of the American Society in 2004. He got a Humboldt Award in 2007. He got a very prestigious ERC Advanced Grant in 2008, and he won the EPS Prize for Quantum Optics and Electronics in 2013. We are now all very excited to listen to Maciej's talk. Please.
Thank you very much for this very nice introduction, and thanks very much to the organizers that have given me opportunity to give a plenary talk here in this beautiful city of Toledo. As already mentioned by the chairman, I work in Barcelona. My salary actually is paid by Icpeac. It's Institució Catalana de Recerca en Estudis Avançats, Catalan Institution for Research and Advanced Studies. For those of you who know European financing system in science, this is very much analogous to French CNRS. Centre National de Recherche Scientifique, with one difference. Icpeac, in 12 years of its existence, have given about 250 permanent positions in all sciences and even in some humanities in Catalonia. So it's similar to CNRS, but it's very elitary. Now, these guys who got salary from there have to be installed in the institutions, and I'm installed or affiliated fully with ICFO, Institut de Ciencias Fotónicas, Institute of Photonic Sciences, which is one of the centers of excellence in Catalonia. Now, again, making analogy to European system, this would be analog of Max Planck Institute in Germany, in the sense that we are financed by a private foundation, which has in its members public bodies like local government of Catalonia and universities and so on. So it's somewhat similar to Max Planck Gesellschaft, except that it doesn't have so much money. So the effect is that we have to fight for all these grants. I even got a second ERC grant last year. When you get these grants, then you can start to work. So I'm going to talk about the new subject, which is called Toward Atto-Nanosecond Nanophysics. And I apologize to the experts in the area. This will be more like tutorial talk, because this is I understood that this is a very wide audience and very mixed audience. So I will try to be very elementary. Only at the end, maybe I will say some things which are more technical. So coming back to this funding, the results are not bad. I have a theory group which has like 25 people because I collect all this funding from these places. Most of the subject that we study is called atoms, quantum information, as was mentioned by the chairman. At the moment, there's only one person working on attophysics, but we have very strong collaborations with the experimental group at ICFO, and also with people who used to be in our group and now are in other places. In particular, Marcello Ciappina played a very essential role in studies of this atto-nanosecond physics, and his name will be mentioned in this talk very often at the end. So the outline of the talk is the following. I will start talking about conventional intense laser matter physics and attosecond physics. And this will be really a kind of tutorial. I will talk about the three processes which are some of the most important processes in this kind of physics: high harmonic generation, above threshold ionization, and multi-electron ionization. I will then explain you the standard simple MEMS or three-step model, which also has been mentioned several times, in particular yesterday in the talk of Robert Moshammer and others. And I will then talk about typical numbers. And then I will give you a kind of spirit of what I understand and what others understand by atto-nanophysics. So I will talk about the selected experiments. Most of the things that I will be talking about are maybe 2 years old already, so they are somewhat established. There are much more experiments on the scene right now, but I will just tell you about a few, just to give you some examples. And finally, I will talk a little about the theory. This will be the more technical part in which I will talk a little about theoretical approaches and the results. I will give you again only 2 examples of the results in this direction, and maybe talk about some new effects which we have studied in the last month. Okay, so let me go to the conventional intense laser matter physics. So the typical process that you study in this kind of physics is high harmonic generation. How does it look like? So it looks like that. You have atoms which can be jet of noble gas atoms, supersonic jet, for instance. You shine, you focus the laser on them, and you see what comes out. What comes out are high harmonics, as the name says, and they can be very, very high. And then you analyze them spectrally, or you analyze angular resolution. Well, you do the typical as good detection and as rich detection as you can. These harmonics are high harmonics, so they come in the regime of frequencies which range from XUV to even soft X-rays. So the typical spectrum of high harmonics looks like that. They have, first of all, discrete frequencies because they are harmonics. Typically, in the simplest experiments, only odd harmonics are produced because of rotational symmetry of atoms, but you can have situations in molecules or other situations where you have also even harmonics. But anyway, so the spectrum consists of peaks, and then it has typically the following form. So relative intensity of the spectrum of harmonics looks like that. For first few harmonics, it goes down. Then there is a very long plateau and a relatively rapid cutoff. Now, if you use the long short pulses, long short pulse would mean, say, 30 femtoseconds or 100 femtoseconds, something like that, then you really have a very nice spectrum in which discrete harmonics are resolved. And the funny thing about them is that if you take few of them, it turns out that they come out locked in phase. So if you look at the temporal behavior of the signal that comes out as a combination of few harmonic modes that have more or less the same intensity in the plateau and that have locked phase, the outcoming temporal shape of the XUV field or even soft X-ray field consists of a train of attosecond pulses. Okay, so this is very simple. If here the typical period is 1.2 femtosecond for 800 nanometer laser, then you will have to divide it by the number of harmonics that are involved into this train in order to get the width, the temporal width of the members of the train. So if you take 10 or 20, you will have 1.2 divided by 20 gives you 60 attoseconds. That's why you call it attosecond pulse train. Now, if you have, sometimes you have different situations in which in the cutoff all the harmonics do not come in really in the form of the discrete peaks, but rather there is a kind of continuum here at the end, a continuum spectrum, and then you can generate single attosecond pulses. And many people have worked on that, and there is really a huge activity in the last, let's say, 20 years. The second process that I would like to talk about, mention, is about threshold ionization. This was, in fact, probably the first process that initiated the whole physics of super intense laser atom interactions. So here, again, this is an ancient figure that I took from Wikipedia, I guess. And then modern experiments, remember the talk yesterday of Robert, for instance. The modern experiments look much more sophisticated, and in particular, detection is much more sophisticated. But roughly speaking, the phenomenon that we're talking about is that, again, we have a laser beam, we have atoms in the laser beam. In this case, if the laser beam is polarized in this direction, the electrons mainly get ionized and get away in the direction of the polarization, and then they are detected here. What is detected is, in the first place, their kinetic energy or energy, and in the second place, angular distribution, if you are clever enough, or even correlations, if you can do sophisticated measurements like CORTRIM, like Rabbit, and things like that. So again, if you look at the spectrum, it consists of the peaks. If you use the multi-photon language, the peaks corresponds to amount of photons absorbed by the electron to get energy above the threshold for ionization. So you have these peaks like that. Well, here it's not so regular. In fact, the low energy spectrum has a lot of structure, which was discussed yesterday in the lecture by Robert. But then, however, the spectrum also, it doesn't have maybe plateaus, but it has some kind of extended, slow decaying peaks, okay? Now, the third process that I would like to talk about is multi-electron ionization. Again, the idea is very simple. if you think in the language of multiphoton ionization, you start with the neutral atom, you absorb some number of electrons in order to ionize one electron, you go to one electron continuum, and then from the ionic ground state, you absorb even more, maybe photons, and you go to two electron continuum. So this would be a process of two electron ionization. If you look at the spectrum, in this case, it's not really a spectrum, it's rather an ion yield as a function of intensity of the laser. So this is the rate, the number of produced atoms. Well, if you go, this is the one electron ionization, this is two electron ionization curve. Now, if you go to low intensities, this curve here in log-log scale is linear, which means that we are in the multiphoton regime. The ionization is proportional to the certain power of intensity corresponding to the number of photons necessary for the ionization. But then it bends. And this bending is related to the appearance of other mechanism of ionization, which is tunneling. And the theories of tunneling, well, they agree relatively well with this sphere. But if you go to the yield for the two electrons, then you see that there is something else. Here, the last part agrees quite well with the tunneling theories, but here, for smaller intensities, you have something, well, here there is still multi-photon part, but there is some curved structure here, which in the literature when I was young and beautiful was known under the name of a knee of Anne Lullier, because Anne Lullier was the first person to measure this. And it looks like a knee. Okay, so that was a puzzle for several years, actually. Okay, so let me now try to explain all this physics in terms of the very simple and useful, in fact, model, which is called three-step model, and which was introduced essentially in '93 by Paul Corkum and Ken Kullander and his colleagues. I mentioned here this paper in which we have, so to say, generalized this model into quantum, so to say, or semi-quantum picture. So how does it work, this model? You have an atom. You can think about essentially the situation in which only one electron in the atom is active. So this is called single active electron approximation. Obviously, if you go to stronger intensities, there will be more electron active. In particular, if you want to ionize two, maybe you will have to take into account correlations. But let's start with the simplest thing. We are going to talk about high harmonic generation. Single electron approximation is very good here. So what happens is electron is in the ground state, but it's in the laser field. Now, the laser field couples to electron via dipole interaction. Both the size of the electronic wave packet and even the size of the electronic excursion, if it will oscillate in the electric field, are smaller than the wavelength. Therefore, you can think about the interaction as being dipole in the electric field. And the electric field is essentially constant in space. It just depends on the time it oscillates. And therefore, it provides a linear oscillating potential for the electron, but oscillating slowly because we are considering the situation in which the wavelength is large, or if you wish, frequency of the laser is slow in comparison with characteristic frequency of the electron in the ground state. So then you can think about this as a kind of quasi-static picture. When the electric field is huge as its maximum, then the potential looks like that. It's a Coulomb part and then the linear part, which allows you, of course, for this electron to tunnel out because the barrier is finite and it's not very high if the electric field is high. And this is what happens. Electron tunnels out in the first step of three-step model, but then it is essentially free of Coulomb potential. It feels only the strong laser field. And is accelerated in the strong laser field. In the strong laser field, it oscillates. In particular, it can turn back, come back to the parent ion, and recombine. And this recombination is the process in which the high-frequency photons are produced. In fact, however, during this process of acceleration, the electron gains some kinetic energy. which is usually expressed in terms of ponderomotive energy. Ponderomotive energy is given by this formula: electric field, charge, mass, frequency of your laser. This is just the average kinetic energy that oscillating electron has in the electric field of the laser. So this is, it gets kinetic energy of this order with some prefactor, which is really a classical, the number that comes from analysis of classical trajectories of the electron. And then you can very well estimate the cutoff in the harmonic plateau. It corresponds exactly to this energy, well, plus ionization potential. Relatively simple calculation shows you that this has to be like that. Okay, so this explains that classical physics is responsible for this cutoff here. It doesn't say much about, it also says why the cutoff is persistent so much, because there are classical, so to say, trajectories of electrons that can contribute to that. And remember again the lecture by Robert yesterday, who used classical physics very extensively. So let's go now to the ATI and try to explain ATI in the same manner. So ATI spectrum usually looks like that. It has, again, a part that decays relatively quickly in log-logs, in logarithmic log-lin scale, and then kind of plateau. It's not really a plateau, it decays slowly, but it can have even several of these kind of bumps here, which extend to higher energies. In fact, this first decay part is a part which extends roughly to 2 UP, sorry, and this one to 10 UP, roughly. Now, how can you understand it? I'll give you a picture from some other paper. So this is, again, the spectrum of electrons as a function of electron energy, logarithmic scale, linear scale. You have this fast decay, then first bump, second bump, third bump. Here, this is for xenon in elliptically polarized laser field. So the classical dynamics is a little more complicated, but you see that to each of these bumps, there is a family of classical trajectories describing the corresponding to the process that is responsible for these electrons produced at these energies. So this peak corresponds to direct tunnel ionization. The electron goes away from the atom and never comes back. The pink part corresponds to electron going out, making an oscillation and recolliding on the atom, and then getting a bigger kinetic energy. I told you that if it would be only this, it would get not more than 3.2 or something. But now, after a recollision with the atom, it can get up to, I don't know, 10 or something like that UPs. And in this case, there are even different other parts of the spectrum. If you have different bumps that corresponds to different, let's say, topology of trajectories of electrons that goes away from the atom, makes some oscillations, recollide on the atom, and goes with the higher energy away. Let me go to the multi-electron physics again. You can think about this process again in two manners. One is that you have an atom, you detach first electron, it goes away, and then you still have a laser which detaches the second electron, and you have two electron ionization. Okay? This will be a sequential ionization. But there is the same mechanism possible as in the case of ATI, or high harmonic generation. You can have a first electron to be ionized, go into a continuum, oscillate or being accelerated and decelerated in laser field, coming back to the parent ion, being rescattered, and at the same time kicking out the second electron. And this is a collisional ionization. And if you look at data, it looks like that this knee of Anne-Loulier in fact comes from the processes that corresponds to this recollision. So electrons go out, comes back, kicks out the second electron, itself gets some high kinetic energy, but part of this energy is transferred to kicking out the second electron, okay? And this is responsible for this part of the spectrum, whereas this part of the spectrum corresponds to the tunneling of a second electron just in a sequential process. So first electron go out here, the second there, and that's it. They are essentially uncorrelated, whereas here, obviously, they are correlated. Okay, so let me summarize this. Maybe I summarize it first with this sentence. In all this conventional strong field physics, single atoms field specially homogeneous laser field. This I said already. Dipole approximation is good. The wavelength of the laser is much bigger than characteristic length which electron feels. The size of the ground state, the excursion amplitude in the laser field, so amplitude with which it oscillates. Does it mean that inhomogeneities of laser field do not play a role? Obviously not. And here I come back to this picture, which is actually from our science paper many years ago, already nearly 15 years ago. So if we talk about threshold ionization, the first thing you have to take into account if you want to compare experimental data with the theory, you have to take into account that the electrons comes from a focal area of the laser. And in the focus, the intensity of the laser depends on the position. Obviously, it's 0 at the end, and it's the biggest in the middle. So if you want to compare any kind of theory with the experimental data, you have to average over the distribution of the intensities. Okay? That's obvious. So this is one thing where inhomogeneity of laser field obviously plays a role. Even more, when electron leaves the focal region, it gets additional acceleration due to or it may get additional acceleration due to the so-called ponderomotive effect. Roughly speaking, it gets this average ponderomotive energy that he had inside the laser field, and when it goes out, it doesn't have it anymore, or it has it in the form of the kinetic energy. And these things have to be taken into account, obviously, if you compare theory with experiment. Another thing is a question of phase matching. You see, if you want to have efficient harmonic generation, it's not only enough that single atom produces a beautiful spectrum that in the plateau extends even to water window. No, you have to have many emitters that collectively collaborate one with another. What does it mean? That the phase of this emitter has to match with another and another with another. And phase matching is very important. Phase matching means phase relations. Each of the single atoms that produces harmonics has its own phase of its dipole moment, which is dynamically induced by the interaction with the laser. But if it's in the focus of the, let's say, Gaussian beam, the Gaussian beam also has a phase, which is a, and now French people should help me. Gua? I don't hear it. Gui phase, which goes not so much, it goes, well, it goes as much as it can from, let's say, minus pi to pi on this side. And of course, these two phases interfere. And therefore, this is maybe not so surprising that when you put atoms here in before the focus or outside the focus or in the focus, different contributions to high harmonic generation like to be phase matched. And in fact, when you look at the spectrum as you move from before the focus to after the focus, the angular, this is even the spectral composition of the harmonics. This is, I guess, 19th harmonic generated in neon. You see changes completely from single peak to several peaks. Okay? And this reflects the situation in which, in the simple case of single peak, there is only one electronic trajectory, and very simple, that corresponds to the process, whereas behind the focus, there is also one electronic trajectory that corresponds with good phase matching to the process, but it's much more complicated trajectory, so the spectrum is more complicated. Okay, so still, this sentence is true. If I look at the response of a single atom to the laser field, I can very safely assume that the laser field has a given intensity and does not depend on the position of the electron. It depends maybe on the position of the atom, because if the atom is outside of the focus, then it doesn't feel any field. But if whatever the field in the point where the atom is spatially homogeneous. So let us look at the number. Classical electron excursion. Yes, we will estimate the classical electron excursion in oscillating field, the so-called quiver radius for different lasers which are used notoriously nowadays. 20 years ago, it was essentially Ti-sapphire and neodymium-YAG. Now we have a lot of work on longer wavelengths. And okay, so for this guy at 10 to 13, the quiver radius is of the order of less than nanometer, or it approaches, well, it's linear in, sorry, it goes like square of intensity, so it's, it goes a few times more for 10 times bigger intensity, okay? For these lasers, it's of course a little bigger. Why? Because the frequency is smaller, so you get a square factor in frequency here. So the wavelength is, roughly speaking, factor 2. So you get factor 4 in the frequency, and then the quiver radius is again of the order of nanometer or few nanometers. And if I go to the highest wavelength, it's still I go from, let's say, 4 to 10 or 20 nanometers maximally. So all these numbers are obviously much smaller than the wavelengths, and much smaller, and that's why I can typically use the dipole approximation with the constant position-independent electric field to describe response of single atom with the laser field, okay? The situation will be, however, different if my electric field would start to change on the scales which are comparable to this excursion amplitude, okay? And this is possible in nanostructures. And this is what starts my, the main part of my talk. So the idea here is that there is some kind of new science being born, which is a combination of using ultra-fast laser pulses, the ones that are used in attosecond physics, and combining it with the nanostructures and looking what it will give. So the first paper that was on the market is a Nature paper from 2008, if I remember very well, by the Korean group of Seng-woo Kim. And this is a paper in which, again, they have used this kind of nanostructure. They had a bow tie structure. The laser that shines on this kind of structure is not very intense. It produces, however, nanoplasmons on the surface of this nanostructure. These nanoplasmons produce themselves evanescence electric fields, in particular in the space between the bow tie, parts of the bow tie. You can have electric fields that are very much enhanced with respect to whatever you put here. So you can get enhancement factor theoretically up to 1,000, okay? So you can put a field of 10 to 11 watt per square centimeter here, and you get 10 to 14 there. Of course, this is theoretically, and theory is unfortunately not so easy. It's not so easy to describe all the aspects of physics of such systems. So the guys in Korea, what they propose is to take this, put the atoms here inside, look at harmonic generations from atoms, make an array of these bow ties in order to assure the phase matching and things like that, and see what comes out. And they had very promising results in two aspects. One, extending spectrum of harmonics to higher frequencies, and extending efficiency of production of harmonic to higher efficiencies, okay? However, this experiment was never really repeated by any other group, and people were saying that the mechanism maybe of what they see in the experiment is different, and many people were trying to repeat it and recover it, and no one essentially succeeded. We also have tried an experiment in ICFO where we joined a group of nanoplasmonics, and now this time goes down or up. Chairman, because he's 25, so it goes down. Goes down. Now I see it. At 25 is difficult to say. Okay, so we also tried to repeat similar experiment with slightly different nanostructures. The problem here is the following. It's very difficult to estimate the threshold for damage for this kind of nanostructures. So you put 10 to the 10 watt per centimeter as is incoming laser pulse, and you get here 10 to 12 watt per centimeter squared. It's not enough to generate harmonic. You put 10 to the 11 and you destroy the structure. And it's not even enough to produce the harmonics, it's painful. And this is what happened in our experiments, okay? But, of course, we had limited number of funds and limited number of time, so we didn't really explore optimization of the shapes of the nanostructures or even material. The ones that were used, I think, in these experiments were made of gold, and our also made of gold. But maybe you can use, I don't know, something different. I'm not a material scientist, but anyway, there is and many people in the last years started to investigate what are the possibilities. The same group with the collaboration of Matthias Klink and Mark Stockman, a year or 2 years later, published in Nature Photonics a paper in which they put atoms inside of the nanotube, and they use plasmons generated in this nanotube to, again, enhance harmonics. And this is accepted. I mean, this is already one of these experiments that belongs to the area of atonanophysics and do not generate such discussion as this one. Let me show some other examples. So apart from harmonics, you can think about generating electrons of high energy from this kind of systems. And again, this is the letter to Nature by Peter Hommelhoff, in which he generates electron from the nanotube. So again, he shines a laser on the nanotube, there are plasmons generated, and some of the electrons leave this area, and they can get quite high energies. Very similar very similar experiment led by Matthias Kling in Garching. So Ferenc Krauss is on the paper also. So here they use dielectric nanospheres, and again they excite the plasmonic excitation inside of the spheres, and then they look on the electrons that are emitted from them. Okay. The generation is using a controlled few cycle ultra short laser field in this case and in all of these cases essentially. Another example is another electron emission from nanotubes, this time by another group, by Herring, Solly, Gulda, and Ropers. Another letter to, I guess, nanophotonics or something. They have a nanotube, and they look, they shine the laser on it, excite plasmon, and see how the electrons go up. The main conclusion of all these experiments is that you can control electrons that go out, and you can produce electrons of higher energies than in a standard ATI. So let us now talk a little how to describe this kind of situations. What do you have to add to the conventional description of single atom response or two atom response in order to treat spatially inhomogeneous fields? We have to couple now, we have to couple electron to the laser field, which depends on the position on the scales which are smaller than wavelength. This is the whole thing, that most of these plasmonic fields are evanescence fields, so there is no problem that they change on the scales that are smaller than wavelength. So one approach is, of course, purely quantal. You solve the time-dependent Schrödinger equation. This is what you do also in conventional physics. Typically, you always start with 1D models in order to understand qualitatively what's going on, and then you go to full 3D simulations. If you have situations in which these nanostructures define some boundaries in your space accessible for the motion of electron, you assume that the electron is absorbed on the surface of the metal or whatever is there. This is simplifying assumption, which maybe can be also relaxed to some extent. And then you calculate ATI and OETI or ion yield or high harmonic generations by just processing the data. So the only difference in this approach is now electric field is not just a function of time, it also depends on position of the electron. Well, you can use the semi-classical approach. In the semi-classical approach, what we use frequently, sorry, because this slide was prepared by Marcello Ciappina, so I shouldn't do that. the strong field approximation, or models that, in a sense, use the asymptotic form of electron behavior in the strong laser field. One formula was again shown yesterday in, I guess, in the record, in the lecture of Robert again. It was the formula in which what happens is that you have to describe how the electron gets to the continuum. If you calculate the amplitude of what electron does, is it goes into the continuum, interacting with the laser field, but then in the continuum undergoes propagation. And propagation is essentially semi-classical. It's described by the exponents of the classical action of the electron on the trajectory that it follows. This is not completely true, and I will come back to that in a second. But the main assumption of the strong field approximation is laser field does not affect, I don't know why it's written here, the main assumption does not affect the electron in the continuum. The laser field obviously affects the bound electron in a sense that part of it is moved to the continuum. And then here the advantage of using this is that you have this interpretation of both processes in terms of classical or quantum orbits if you are a little more sophisticated. And this goes makes kind of complementary approach to the more exact approach here. And finally, you can use a fully classical approach, in which you simply solve Newton-Lorentz equations for the electron in 1D or in 3D, whatever. And then this was used again yesterday in the progress report lectures. Classical theory described quite nicely the qualitative and even quantitative aspects of many of these experiments. And the three approaches give comparable prediction, at least for the problems that we have been studying. So I give you two examples of the things that have been studied by us. One is from this PRL, beyond carbon K-edge harmonic emission using spatial and temporal synthesis laser field. So when I talk attosecond nanophysics, I really talk about control of the control of space and time. So what we propose in this paper is really that there are two things. Concerning the electric field and the time dependence of the electric field, we use actually here two delayed pulses. Both of them have an envelope which is described in this case by sine squared, whatever. They have some envelope. They have essentially correspond to n periods of the laser. They have controlled carrier phase amplitude. So in this case it's 0, and in this case it's phi. And this pulse is actually delayed with respect to that. Okay, and they have the same electric field, the same intensity. But on top of that, we assume that this electric field time dependent has also some linear dependence on the position. This is one for the, we assume only one-dimensional thing. So why is it linear? Of course, if you think about this bow ties or something like that, the electric field in those structures will have some nonlinear behavior in general. But if you assume that this dependence of the space is not too strong, and it only starts, let's say, to be comparable with electron excursion amplitude, then you can linearize the dependence, and you can, as a beginning, study this kind of model, and that's it. Of course, we studied also much more complicated. I will come back. So this is the result, and the result is striking. This is the harmonic intensity in logarithmic scale. This is the photon energy. So typical cutoff for harmonics would be here if I would have no inhomogeneity. This is done for quite small inhomogeneity. But whatever these units mean, it's small, but it's not so small. Okay, it's suddenly we get a huge extension of the harmonic spectrum. Maybe in terms of efficiency, it's not so spectacular, but still, I mean, we extend by from, let's say, 300 to 1,100 electron volts. So it's quite a big approach. Now, here in this part of the spectrum, you see that the spectrum is quite irregular. Why is it so? Because there are many electronic trajectories that correspond to the harmonic generation, and they interfere on the quantum level. And this interference typically is not constructive. It can be constructive, destructive, but it gives this kind of chaotic-like picture of the spectrum here, okay? Here in this part, it looks like it's much more regular, the spectrum, and therefore one can guess, and this is indeed the true, that here there is only one electronic trajectory that corresponds to the spectrum. So one mechanism that you have in this process is that some of the electronic trajectories, when you go to inhomogeneous system, are simply gone. And this is because electron goes away in the right direction and never comes back, because it gets into a region when this inhomogeneity is stronger and it pushes it out. Okay, so this explains a little this. But why the whole thing is so much extended? The only explanation that we have found so far for this is the following, that if you think about the propagation of the electron in the continuum, as I told you, is described essentially by a classical action of the electron, or exponent of I times classical action of the electron on the corresponding trajectory. This is not, however, completely true, because electron, in order to get to the continuum, have had to tunnel before, to have tunneled before. And therefore, the real, or the trajectory that you should consider, it's not really just a real number solution of the Newton equation. It's a complex trajectory that takes into account the fact that the electron passes through the forbidden barrier. The imaginary part of the action of electron, which then appears naturally, is related, for instance, to the thing which is called tunneling time, which you may like or may like, but indeed it is that time scale that is necessary for electron to tunnel. Now this tunneling time, or tunneling related to tunneling probability also, obviously depends extremely nonlinearly or exponentially on the intensity of the field. So if you change the field even a little, electron might perform tunneling not in the place in which the field is even changed a little by this inhomogeneity, and get enormous enhancement of ionization probability, and then get another, so to say, augmentation of the harmonic generation. I mean, this is the mechanism that we understand is responsible. This is another example. This is an example in which we really took the people who are on the paper. Romanki Down is a group leader of the quantum plasmonic group in ICFO, and Jens Bigert is an experimental leader of attosecond. So the two groups contributed to experiment and to this theory paper. Unfortunately, I told you experiment never worked, but theory did. And in the theory, what we do, we take the bow-tie structures that we used in the experiment. We calculate electric field exactly how it is here, using finite size element, and this was done by this guy, Serdian Achimovic, who was a postdoc with Roman Dan and specialist on plasmons. So we calculate electric field here. We assume we put the atom here. So electric field has this profile, more or less. This is this is how it looks like. So indeed, if I put the atom here, it's more or less linear, but if I put here, it's more like quadratic. And we calculate using time-dependent Schrödinger equation the spectrum, assuming that there is a corresponding plasmonic enhancement by factor, I don't remember, 100 or 500 or something like that. We see a clear enhancement of the extension, of the spectrum of harmonics. Not so spectacular as in the previous case, but still quite spectacular, from 130 to nearly 200 harmonic orders. Unfortunately, as I told you, this didn't work because this bow tie melted out before we reached the intensities necessary for the thing. But still, it was very promising to look for the thing. So let me finish with just mentioning few papers that we wrote in the last year, essentially, or that we are working on. This is in preparation. So one of the ideas that we are following is to combine all that, so temporal control and spatial control, with a situation in which the ionization potential is not so strong, or we have weak binding. So obviously, if we study, for instance, negatively charged ion, so in this case hydrogen ion, then this negatively charged hydrogen ion is the first electron to go, so to say, is weakly bonded, and at lower intensities you can reach effects that involve 2 electrons. Okay, so enhancements of 2 electron effect. So let me show one figure from this. Let me or not let me, there. So if you look at these figures, this is again harmonic spectrum as a function of harmonic order, I guess, and this is intensity of the harmonics. And here the inhomogeneity of the laser field is essentially 0. And the blue line is a solution of the time-dependent Schrödinger equation for 2 electrons. This is in 1D, so it can be done. And the red line is for 1 electron. Single active electron model with the Hartree-Fock corresponding Hartree-Fock potential. As you can see that already without inhomogeneities, there is a lot of difference between the 2 spectra, which is related to the fact that 2 electron effects are indeed important in this problem because the first electron is relatively weakly bounded. Okay, so already here you have big difference for relatively small harmonics. But then if you start turning on inhomogeneity, which are these 2 lower figures, you see that not only for low harmonics you have differences, but you start to have differences in the tail of the spectrum. You start to have to produce, at this moment not yet efficiently, but more and more efficiently, harmonics with very high energies, which are not present in single active electron calculations. So this is one of the things that we think inhomogeneity in the field, so in the plasmonic field, if you wish, might enhance multi-electron effects and correlation, which will be very interesting. The second example that I want to show is a paper that was published this year in collaboration. So again, Marcello Ciappina was the leader, and Ferenc Krauss was, and several big shots were on the Ferenc, Luis Rosso, on the paper. So the idea was, again, small ionization potential, weak binding. So what we study here is actually alkali atoms, which are known to be very bad for high harmonic generation because exactly of this reason. The high harmonic generation is, of course, occurs only if the electron comes back to the parent ion. That means the ionization cannot be complete, it has to be weak. Okay? And in this case, ionization is very strong. And therefore, but what we do here, we compare potassium and sodium, and in potassium we do the kind of resonant excitation with respect to one of the internal bound states. And we observe the effect of the so-called carrier wave Rabi flopping, which I will explain on this figure. I have still 1 minute, 20 seconds. So in the standard 2-level problem, if you think, so we think about the ground state and the excited state, which is resonantly coupled by the laser. If you apply a 2-pi pulse or 2n-pi pulse, in the situation in which the Rabi period is much larger than the driven light period, then what happens that the population goes from ground state and comes back to the ground state because area of the pulse is 2-pi. Now, if you do the same thing in the situation in which the Rabi flopping, and of course the block vector oscillates in the perpendicular space, but oscillates up and then go down, and the population comes back to 0. But if you have a situation in which the Rabi period is not much larger than driven light period, then the area theorem is not true. You come back not to the ground state, but you have some non-zero population here and things like that. And this is what we think happens in, or may happen in, if you shine resonantly laser on potassium coupling, I don't remember which states, which were 2s to p or something like that. Then you, if you look at the third harmonic generation, so high harmonics are not produced here, you look at third harmonics and you increase this intensity, you suddenly, in the peak of third harmonics, start to see a very complicated spectrum, which is related to this carrier wave, Rabi flipping. So most of the papers that we have written in the last 3 years are led by Marcello Ciappina, who is here, he's on all of these papers, I guess. The papers that I talked today are this one about the bow tie structures, and this piece of letter about helium, and these last two about the recent research. This is Marcello, who is here, and these are people who were involved in this project. I always, when I Google Roland, I get this, but I like this piano, so I keep it. And okay, that's it. I mean, this is about ultra cold atoms, but there is something about the ultra fast science inside here, and it's cheap. This one is even cheaper, and it's more important. There are many aspects of my talk which are related to what Ahmed was presenting in his lecture. Of course, he was also talking about shining short lasers on nano tubes. Here in this is about Polish jazz, but it goes beyond. And beyond is avant-garde music in general and contemporary avant-garde music. A lot of this music is played on micro instruments of the size of millimeters. So if you think about Ahmed, the future probably of avant-garde music is nano instruments. Thank you very much for your attention.